So welcome back friends. So now we'll start with the fifth module of optimization technique, and this module includes the momentum based gradient descent methods, that is ADAGRAD, RMSPROP and ADAM, non-convex optimization, that is convergence to critical point saddle points method. Okay, so let's see. First question is, explain in brief ADAGRAD optimization strategy and RMSPROP. Okay, so both are used to improve the training of neural networks by adjusting learning rates dynamically based on the characteristics of the data. ADAGRAD optimization strategy works by accumulating the sum of squared gradient for each parameter during training. Okay, so this accumulates the sum of squared gradient, that is sum of this squared gradient. This is gradient and squared. Sum of this squared gradient, it accumulates at each steps for the working. Okay, so the equation can be given as gt is equals to gt minus 1 plus gt square theta t plus 1 equal to theta t minus eta upon under root gt plus epsilon dot gt. Okay, so this allows infrequent features to have larger updates, making it effective for sparse data. What is sparse data? Is to going through the data and reading it. Okay, and however, since GT continuously accumulates, the learning eventually becomes small, which can slow down training. Okay, so it can since it accumulates continuously the value of GT, the learning eventually becomes small because it continuously accumulating and the memory will become full and it will slow down. Okay, so the main advantage of ADAGRAD is that its effectiveness with sparsing data. So it can sparse data very effectively. Okay, so a drawback is that accumulate sum keeps growing, causing the learning rate to decrease continuously, making the training slow or even stop. Okay, so next is RMSPROP. So this is an adapting learning rate optimization algorithm that modifies ADAGRAD by using an exponentially decaying average of squared gradient instead of a cumulative sum. Okay, so it adds a exponentially decaying average squared gradient instead of that sum. Okay, so when we use this exponentially decaying average of squared gradient, it can decay over the time and it can overcome this the use of this cumulative sum, preventing the learning rate from the diminishing too much of stabilizing training. Okay, so the equation can be given as et equal to gamma et minus 1 plus 1 minus gamma gt square. Okay, so the parameter update rule can be given as theta t minus 1 equal to theta minus alpha gt upon under root et minus plus epsilon. So same you have to write in exam, just learn it and it will be good. So these all parameters helps model adapt quickly in complex non-convex problems like training the deep neural networks, leading the faster and more reliable convergence. Alright, so now let's move for the second question, difference between convex optimization and non-convex optimization. So according to the definition, for convex optimization, all constraints are convex function and the objective is convex and concave. Convex for minimization and concave for maximization. Okay, and for non-convex, the objective or any constraint are non-convex only. Okay, here the no concept of concave. Properties for convex optimization, it's linear function, and convex problems like linear programming are convex. The property of non-convex is the function involved are non-convex, leading to multiple feasible region and local minima. Okay, so this leads to multiple feasible region and multiple local minima. Okay, the solution characteristics for this guarantees a unique global minimum, making optimization easier. So this guarantees the local minima exist. Finding the global minimum is more challenging because if multiple minimum exist, then it is very tough to find for the exact one global minimum. Okay, we have to iterate for all the phases, making it further inefficient. Computational aspect, generally easier to solve due to complexity, algorithm and are well understood and guarantees convergence under certain conditions. Okay, and this one more computationally challenging, requires sophisticated algorithm to explore the solution space and avoid local minima. Okay, so the example for this convex optimization is, it is widely used in ML engineering, economics and operational research, whereas for the application of non-convex optimization, it is widely used in deep learning, molecular modeling and financial modeling. I hope this difference is clear to you all. Just read it. And the third question is saddle point problem in machine learning. What is saddle point? As I told you earlier also, saddle point is a point where there is no minimum or maximum point exist. Okay, so let's see that saddle point in machine learning refers to the presence of point in optimization landscape where the gradient is zero, but the point is neither a minimum nor maximum. Okay, instead it's a point where the surface of the cost function resembles a saddle with some dimension curving upward and other downward. Okay, so visually this is the if you visualize this, then some of the dimension curving upward and other is downward, so saddle point will never come. So this is the saddle point in between. Okay, key characteristics include the gradient of the cost function of the saddle point is 0. The point is not a minimum or a maximum, so this is not a minimum or maximum. The surface is flat in some dimension and steep in other dimension. As you can see, dealing with saddle point involves strategies like higher order optimization method. You can use NR method, random initialization to escape saddle points. Okay, injecting randomness or noise into the process, applying techniques like gradient clipping and momentum to traverse flat region more effectively. So this all is about the saddle point. Now let's move to the next question, that is write short note on stochastic gradient descent with momentum and ADAM. So what is stochastic gradient descent with momentum? It is the SGD only without extra momentum term. Okay, so SGD with momentum enhances the basic algorithm by adding a velocity term with it that accelerates and updates in relevant direction. Okay, it accelerates and updates in a relevant direction. You can take an example of a ball rolling from a hill, that rolling from the top of the hill, when it is coming into the path, it avoids all the obstacles. Okay, because of the momentum of the ball, it avoids all the obstacles. So same example you can take here also. As you can see, the equation for SGD is this, but the equation for SGD with impulse is this. So this is the extra momentum term, and because of this after the epsilon, Vt plus 1 is get added in spite of this one. So Vt plus 1 means this all terms. Alright, so it's been added into this, giving the result of theta j. The momentum term act like a friction or inertia, allowing the optimization to move faster along consistent gradient direction and escape the shallow and low. So similarly, I give you the example of the ball, which a person dropped the ball from the hill. Then while it comes to the path, it avoids all the obstacle. Okay, so the same you can relate with it. Now, seeing the next is ADAM. Okay, so this is popular optimization algorithm that combines the benefits of momentum based updates and adaptive learning rates, that maintains estimate of both the first moment and second moment. Okay, so this is the equation which we'll see here. The first moment equation is this and the second moment equation is this. Just try to figure out the similarities over here. This is M and this is V. T plus 1 is same. B1 MT, B2 VT, plus in place of M it's V, so B1 MT, B2 VT. That is not B, it's beta actually. So beta 1 MT, beta 2 VT, plus 1 minus beta 1 is same, 1 minus beta 2, and that is delta theta L theta, delta theta L theta square. So this is RMSPROP and this is for impulse. So this will estimate the both the first moment and the second moment. Okay, so the first moment and the second moment, and you have to remember this all for writing an exam. Okay, so ADAM adaptively scales the learning rate for each parameter, leading to efficient and stable convergence in training deep neural network. Okay, so that's all, and let's move to the sixth question. What is the best optimization algorithm for machine learning? So this is very easy one. In general, a normal gradient descent algorithm is more than sufficient for simpler tasks. If not satisfied with the accuracy of the model, we should try RMSPROP or add a momentum term to gradient descent. Okay, we should always try RMSPROP, or we can add a momentum term into the gradient descent also. Okay, however, ADAM is the best neural network optimization algorithm available today. best algorithm for almost any deep learning network. Okay, especially if we set ADAM hyperparameters to the following value. This value you have to remember: beta 1 equals to 0.9, beta 2 is equals to 0.999, learning rate is equals to 0.001 minus 0001. Okay, so ADAM and the above values of the hyperparameters are a very good starting point for any problem and virtually any types of neural network architecture. Okay, for same reason ADAM is default optimization algorithm for any deep learning problem. Only in few cases we shift to RMSPROPs and ADAGRAD, etc. So I hope this clear to you. Okay, so just learn all these 6 questions, and with this we have completed all 5 modules of optimization technique. So all the best for exam, and thank you for watching. Bye bye.